That's for that wave number. Excuse me, it's in the R direction. That's not, yep, that's right. Minus omega t. And it's reflected, so V1 is the velocity on this side still. So we're going to cross this term here with the wave, with the basically the direction it's going from the pointing vector. Cross it. Okay. And a transmitted wave. And transmitted is going to be equal to t minus, excuse me, dotted with these directions going, wave number there. Minus omega t. This is going to be equal to V2 because it's in that second medium now. It's from the air to the water, air to glass. It could be glass air. Normally, a lot of times we just say air and water. It's just, or air and glass. Just convention. Transmitted unit vector for the wave number. Cross that with this electric field vector there. Okay. All right. What I'm going to say is all waves have the same frequency. It's conservation of energy. Wavelength will change in this medium, but the frequency's got to stay the same. The frequency is a function of energy. Conservation of energy says that must be true. That's probably a proof or an explanation for another day. You can Google that and look that up. That means that these wave numbers, K1, V1, has to equal K, excuse me, incident V1, the K for the reflected times V1 has to equal the value, and that equals E omega. That's the angular frequency of it. And if you say that, what you can say is, of course, these two, and that means these are the same. And then it also means then that the incidence, which equals the reflected K values, these wave numbers, is going to equal to, if you do this ratio, if you solve it, V2 over V1. If you do that in terms of N, remember what we showed it was previously. N1 over N2. So that's the relationship between the wave number going in on side 1, on medium 1, and the wave number in medium 2, that second medium it went into. Now, I like kind of how they do this. There's other ways I've seen this done, and this, if you accept what we do next, it makes the rest of what we do somewhat easier to understand. Now, what it's going to say is, at Z equals 0, we're going to have the electric fields, have to equal the magnetic fields, the electric fields going in, and the electric field coming out, magnetic fields going in, magnetic fields going out. It's going to look something like this. We'll have some magnitude there, e to the I, our input. And then we'll have some other amplitude there, E field, B field, something right here. This would be for the reflected wave. It's going minus omega t, and I keep doing that. And that would equal here E I. Did it again. Minus omega t. And of course, at z equals 0. It's going to look something like that. Where these are just either the, what's in parentheses would be the magnetic field amplitude for transmitted, reflected, or incident, or electric field amplitude, transmitted, reflected, or incident. It says, so what must happen? If this is true, I'll say, for this to be true, I'll say also, because the boundary conditions that we have must hold for all points in the plane at that boundary. It doesn't matter where we're at on this surface, it's got to be on that plane wave coming in versus reflected versus transmitted. It's got to, this basically is across that plane wave here. These K stuff is, it's across that plane wave. If it's going to be valid for all points in that plane, again at z equals 0, that's what this is really telling us, that K value across that plane. Because it's a plane wave coming in. That means then that these have to be equal. Reflected, because it's got to be the same everywhere. So the reflected, whether it's the reflected part for the reflected, for the incident, these have to be the same. And this actually has to be the same as well. So these all have to be the same. 6. Now they go into a little bit. I'll say for all x and y positions. So we're in x and in y. Now if that's true then, if x equals 0, then the wave number in the incident direction, if x equals 0 for in the y direction, has to equal the reflected in the y, and also has to equal the transmitted in the y. And if y equals 0, of course, similar is going to be true. Now, what does that tell us? Now, from this, we can actually, this infers, you could say, a few things. Now, for that to be true then, it said it's a plane wave, but for that to be true, we're going to call this the first law of first law. They don't say, they just call it first law. It really be first law of waves at a surface, excuse me, at a medium at an oblique angle. We're going to say then that the incident wave, reflected wave, and the transmitted wave all form a plane normal to the surface. Now, I've been saying this is a plane wave coming in. Honestly, it's because I knew what we were getting out from it. Coming in, when we initially started over here on this side, over there, all that stuff, it wasn't explicitly a plane defined. This last little bit at x is 0 and y equals 0, these wave numbers are all the same, so where the wave is at relative to another, all parts of this wave are pretty much the same. It's a plane object. It's not got a different wave number at different parts of this wave. So they're all kind of going together. They're all, hey, come on, guys, let's just go. They're all forming a plane. Forming a line. You could think of it as a 2D line, which is, of course, a 2D line, but a plane. You can also say that this last one here, when it did it for y, the one that did it for y, that means then that if we're going to look at the incident angle, the sine of that incident angle, for that to be valid in y, for them to all be the same, that the y component of that, which would be the y, for the incident angle, the y sine of it would be the y component of it. That's the opposite side of the way we defined it over there originally, because we defined that angle basically. Hang on, let's go back here. So the way I defined it. So y would be out of plane here. Y is out of plane. Okay. What that's telling us is that the sine of that incident angle, which basically would be out of plane for us, these are all going to be the same. Let me define some terms. Theta I is angle of incidence. Theta R is angle of reflection. And theta T is angle of transmission, or that's what we call it based on what we've been doing, but it's normally called angle of refraction. If you took a basic physics course, you've heard this before. Now, for all that to be true, because we know the K values are the same, the angles have got to be the same. That tells us the angle of incident has to equal the angle of reflection. And we get that from right here, because we know that these K values are the same. Those K values are the same. They're on the same side. So the K values have got to be the same there. All right. Now, so this is known as the law of reflection. Now, what we said here previously, and that's on that over there, those are for the x and y components of them. Now, the K values previously, K incident is equal to N1 over N2 K reflected. Okay. I have that. It should be N1 over N2 K transmitted in my notes here. Now, since that's true, These are just the K values themselves. For that transmitted angle, sine of the transmitted angle over the sine of the incident angle is going to be equal to N1 over N2. Now this is known, they call this the third law. And this is, they call this the second law. Okay. And what they find interesting, this is valid. I'll be honest, looking at this, I don't really like the way they set this up, was having it equals. Getting here, you had to go back and see that. When I was looking at it, I was figuring out how to write that. Teachers had to go back and show you that. But they said 3 fundamental laws of geometrical optics. And, you know, you've seen these before if you had a basic physics class. But what's interesting, because we didn't use any special boundary conditions, just for electric fields, these are all generic ones. Any waves, this is valid for any transverse wave. Valid for any transverse wave. That goes from one medium to another, whatever that medium is for that wave itself. Now, next what they're looking about, So let's look at these fields. Now let's start looking at it, taking into account those amplitudes that were in front of those exponentials. So the boundary conditions that we've got to look at, the boundary conditions for these electromagnetic waves, boundary conditions are, let's see, epsilon 1, the permittivity, incident electric field plus the reflected electric field in the z direction. This is in the direction of propagation and it's moving. There's the permittivity. And the electric field, magnitude of that electric field vector in the z direction. Okay. For the magnetic field, z direction. It's transmitted in the z direction. They're just the field vectors add up over here. And 3. We take into account x and y, that's in the z direction, in the xy direction, which is in the plane that these things are off, that this wave is coming in at. That's going to be, excuse me, similar to what we had before, but without that permittivity. That's not saying how much it went, let it go through it. And here, this is the permeability of the material, that first material. That's, forgot to add the tilde there for the complex amplitude of it. And x and y for the B field, that's the permeability of the second material. in that plane. This is the XY plane here that's moving this way. It's Z, X and Y will be like this. And X and Y. Okay. And of course, the initial, the B naught for it would be, of course, 1 over the velocity K hat, that's from the pointing vector direction that it's going. Cross that with the electric field. And that's just from the pointing vector. Okay. Oops, it fell. Let me get it realigned. Okay. All right. So the wave is in somehow an X and Y here. Let's look at a wave that's parallel. That's polarized. Parallel to the plane of incidence. And that would be in the XZ plane. X is up this way, Z is this way. So it's polarized in kind of, which would be really the plane of the board. It would be the plane of the board. So the wave is polarized in the plane of the board. This will be in XZ. So we're going to look at it like that. Notice he lets you do the one perpendicular on your own. If that's now, if we from the boundary conditions, if you do that, before I do that, I want to draw in kind of what we're dealing with here. All right. So this is Z, or X. Of course, this is Z here. The wave's traveling this way. Okay. We've got a wave coming in like this, coming out like that, and then being transmitted like that. What I'm going to say here, let me draw this in black, the wave itself at a point. So right here coming in, got the incident electric field vector, got an incident B field vector, and it's traveling in this direction. That's the direction it's traveling. I'll just do it that way. And of course, these are perpendicular. Here, it's going to be traveling in that direction. The electric field vector is going to be right here. And then the magnetic field vector will be there. And of course, perpendicular. And here, we're going to have the electric field vector going there, magnetic field vector going here, and of course the wave number vector, K, the transmitted, that transmits waves in the direction of propagation that it's going. Do notice the electric field vector was up, now it's laid over. This was kind of like this, and now it's straight up on the B field from incident to reflected. So it looks like they got rotated 90 degrees, or they're out of phase by 90 degrees. This one, it looks exactly the same. So the transmitted wave, it looks like the field vector direction doesn't change any at all. All right, so we're going to apply these boundary conditions to that wave we started out with way at the beginning. Now, if you do that, the first one will give you the permittivity of the first material. Remember, this is one. This is first medium, second medium. Minus E naught incident sine theta 1 theta incident, and they're doing their angles. Theta incident here, theta reflected there, theta transmitted there, okay. Plus, not for the reflected wave, sine of that reflected, the angle of incidence equals E2 T sine theta. And basically all we're doing, we're just applying boundary conditions to our situation. We know this must be valid, and putting in our waves and seeing what we get. That's what we're going to do. 2, if you do 2, basically you get 0 equals 0. So don't worry about that. The magnetic field doesn't have a Z component for it. 3, you're going to get so we're applying this one here now. This was in the first two are in the direction of propagation. The second two are in the plane perpendicular to that direction of propagation. That would be in this XY plane here. And since we're dealing with a wave, it's only in X and Z, we're really going to deal with Y too much. Unless, of course, any cross product that comes into play. So we got reflected cosine of that reflected cosine. Sine would be in this direction here from there. And so for the wave, the cosine of that angle is going to be in the XY plane, in that XY plane. Let's see, reflected. And fourth one is going to give us remember the mu, that comes from, we're looking at B fields, but it's a relationship from it, the B field to the magnetic field, to the electric field vector. So that's that E over V stuff. Okay. So now we're going to apply what we learned previous about these laws, those laws of reflection, those first, second, third law of reflection. Basically, which remember said that basically we get plane waves, angle incidence equals angle reflection. So angle incidence, angle reflection, and then that the ratio of the sines for incidence and transmitted, or refraction of incident and transmitted, the ratio of those sines equals the ratio of the n values, the indexes of refraction. Okay, so if we do that, what we can say then is by the laws of reflection from previous, that should still be in the frame. Okay. Get that the incident amplitude minus the reflected amplitude equals beta becomes a transmitted amplitude. Where, and like before, beta here is equal to mu1 V1 over mu2 V2. You see that's going to come out of that, which was the u1 n2 over u2 n1. And we can also say that comes from that fourth one there. We can also say, I think, from this one here, from the third one. From the third one, we're going to get that. Yep, that's from the third one. Alpha. Now, this alpha equals cosine transmitted over the cosine of the incident angle. And why don't we have a reflected one? What do we know about reflected? Remember, it's the same. So all they did was take this equation here. We know that's the same as incident. Factor out a cosine, bring it over here, and then that's where they took that ratio and let that ratio be equal to alpha. That's all they did with the algebra. All they did with the algebra. And here they just moved this over the other side. That flips, this is underneath, and it goes up on top. And they split that on top, and they just call that beta. It's just making it a little bit simpler to understand, because we're going to need that. So if you do that, from this, so basically we have two equations here, and most of the time we know the incident electric field vector. You know basically what you're putting into a system, right? You want to see what the system does to it. You know, what I put into it, black box. What happens when you come out? You want to see what comes out of it. That's kind of the old standard engineering way of looking at it. You think when it reflects at that boundary is the black box that does something with what we started with. What do we start with and what do we end with? That's really what we're looking at here. Hitting that boundary is something's going on, right? So if we assume these are knowns, if we know what this is, we really have the reflected amplitude and the transmitted amplitude we don't know. But we have two equations and two unknowns. Very simple. Two equations, two unknowns. You know how to solve that. You don't even need to use matrices. You know, you might like that. Probably don't. From this, you can say that solving two equations with two unknowns, you can get that reflected amplitude in terms of the incident amplitude is alpha minus beta over alpha plus beta